Hi all of you. Welcome to another lecture of nanoelectronics. The topic for discussion is effective magnetic field on a crystal and an effect called Aharonov-Bohm effect or we call it as the AB effect. Myself Maria Joseph, Assistant Professor in Electronics and Communication Engineering Department of MPC-CT Pyramid leading the session. These are the topics in Module 5 of KTU syllabus in nanoelectronics. The first topic for discussion is the effective magnetic field on a crystal. In this session, we will examine the effects of magnetic field on a crystal. Application of magnetic fields has significant effects on the crystal. An oscillation of electrical resistivity is basically a function of the magnetic field. Intensity of magnetization also oscillates with varying magnetic field. These effects are due to quantization of conduction electrons under applied magnetic field. With an applied magnetic field along z-axis, the possible energies become En is equal to n plus 1 by 2 into h omega c plus h square k square divided by 2m star E, where n is equal to 0, 1, 2, etc. Where omega c is E into Bz divided by m star E. And we know that omega c is called the cyclotron frequency. Now let us look how can we simplify the equation. It can be shown that in a 2D electron system, the energy spectrum becomes completely quantized. The eigenstates of the two-dimensional system in a magnetic field is given by En is equal to n plus 1 by 2 into h omega c, where n is equal to 0, 1, 2, etc. Now we will look into the topic Aharonov-Bohm effect. Aharonov-Bohm effect is the total amplitude of electron waves at a certain point oscillates periodically with respect to magnetic flux enclosed by two paths due to the interference effects. That is, we can see that it is splitted into two parts. The experimental setup for the observation is shown in the figure. That is, it consists of a metallic ring of diameter 800 nanometer made of a wire of about 50 nanometer thickness. This is the setup for studying the AB effect. The electron waves from the waveguide to the left terminal are split into two waves of equal amplitudes. We can see these two waves go around two halves of the ring, meet each other and interfere in the right part of the ring. We can see they will come together here. Finally, they leave it through the right terminal. A small solenoid carrying magnetic flux phi is positioned inside the ring so that the magnetic field passes through the annulus of the ring. The overall current through the structure from the left port to the right one depends on the following factors. That is, one factor is the relation between the length of ring arms, and the second one is inelastic mean free path of electrons in ring material. This is the AB effect represented in a graphical form. Now, if this relation meets the requirements for the quasi-ballistic transport, the current is determined by the phase of electron waves at the right terminal. The vector potential capital A of the magnetic field passing through the ring is perpendicular to the plane. There is differences in phases of electron waves coming to exit port from different arms. Now, there is a chance of periodic modulation in transverse conductance of the ring by magnetic field, which is known as the Aharonov-Bohm effect. That is, A chance of periodic modulation in the transverse conductance of the ring by the magnetic field is called the Aharonov-Bohm effect. An important aspect of AB effect is the observation that variations in phase can be induced by changing the magnetic field. Thank you so much for your patient listening and hope you will understand this very fast.